Hello again. In this session, we will talk about the force experienced by a charge when moving through a magnetic field. Now, so far we have learned that a moving charge gives rise to magnetic field. But the question is, does it respond to a magnetic field? Well, the answer is obviously yes. Because if you think about it, if a moving charge is generating magnetic field, then that means a moving charge behaves like a magnet. And a magnet will obviously respond to an externally applied magnetic field. So, a moving charge experiences force when it moves through a magnetic field. Let's try and see the properties of this force. So, if a charge Q is moving with a velocity v through a magnetic field which is B. Now, I'm going to represent velocity and magnetic field by vectors. Now, we had said that we'll not involve this, but in this case, let's just briefly discuss this. You know, the arrow on the top of V which I have put is to indicate that this is a vector. The same thing I've done on B to indicate that magnetic field is also a vector. And we have already seen how to find the direction of magnetic field. Now, the force that the charge experiences, the force again I'll show as a vector. The force is always perpendicular to the velocity of charge. So, if a charge is moving with a velocity v, the force will always be perpendicular to its velocity. Can you think of a case where such a thing happens? Remember circular motion? Right? We saw a similar thing happens whenever a particle goes in a circle. Its speed is always perpendicular to the direction in which it experiences force. So you could keep that in mind while picturing this. Right. The second thing about this force is that this force is always perpendicular to magnetic field. So, this force is not only perpendicular to velocity, it is at all times perpendicular to the magnetic field as well. Right. I'll help you visualize this, but let's first list down all its properties. The third important property that you should remember is that the work done by this force is always zero. Now, when I say this force, I mean the force that the charge is experiencing while moving through a magnetic field. Now, the work done by that force is always zero. And this is very easy to prove. Let me show you how. If you recall, we had discussed that instantaneous power is equal to force into velocity. Now, when we do this force into velocity, we consider the velocity in the direction of force, right? So this expression is power is equal to force into V parallel. That is the component of velocity which is parallel to force. But if the velocity is completely perpendicular, then V parallel is zero. Hence, the power delivered is zero. Now, if power delivered at every instance of time is zero, then in any given interval, the power and the work done has to be zero. So, the power delivered and the work done are both zero. We could say because the force is always perpendicular to the direction of motion. So you could also argue that this force never sees any displacement in its direction, and hence the work done by it is zero. Right. Now, combining these two statements, you could say that the force is perpendicular to the plane containing the force to magnetic field and velocity. So the force is perpendicular to the plane that contains magnetic field and velocity. Now try and visualize this. Let's say that a particle is moving in this direction, which is the direction as shown, and the magnetic field is again as shown. Now, the thing to understand here is that V and B are in the same plane. This is the plane in which I am writing, right? So, just like V and B, any two lines always define a force, define a plane, right? So, if you think about velocity, and you know that every vector can be represented through an arrow. So, imagine two arrows, one depicting velocity, the other depicting magnetic field. These two arrows can always form a plane. Let's look at this visualization to help you. I've shown three different cases in which V and B point in different directions. Now, in all cases, see that only a unique plane can be passed which contains both these arrows. Right. Now think of the direction perpendicular. You can see that in all three cases, the plane has only one direction which is perpendicular. Now, this is not one direction but more of one line which is perpendicular to the plane in all three cases. Now, on this line, there could be two directions. Right. So far we have understood that two lines form a plane, and in this case, the two lines that we will use are the arrows which depict velocity and magnetic field. Once we've thought of the plane, there are two possible directions in which the force can act. Like in our case, since V and B are in the plane in which I am writing, the line which is perpendicular is the line which is perpendicular to the screen. And the two directions which are possible are either inward or outwards. Right? Okay. So now comes the way to determine the direction. Now, force will point in the direction when you curl your fingers from V towards B. So, for direction of force, curl your fingers from V towards B. So in our case, if you look at these two, if you curl your fingers from V towards B, my thumb points in a direction which is pointing out of the screen. And so the magnetic field is pointing out of the screen in this case. Let's look at the three examples we took. See how in all three cases we have already identified the line which is perpendicular to the plane. We are left with the option of two directions. Let's imagine a right hand there. Now, see as this right hand is aligned with V and curled towards B, we get the direction through the thumb. So you can see that with this exercise, we get the direction of the force in all three cases. Right. Now, we know these properties of the force and we have found the direction of the force. We have not yet discussed the magnitude of force. So the magnitude of force is given by QVB sine theta. Where we already know what Q, V and B are. Theta here is the angle between magnetic field and velocity. So, a moving charge in presence of a magnetic field experiences a force. We learned that this force is always perpendicular to the direction of velocity. This force is also always perpendicular to the magnetic field. Then we learned because of these properties, this force can never do any work on the charge. Then we found that due to the first two properties, we could say that the force is always in a plane which is perpendicular. The force is always in a direction which is perpendicular to the plane containing B and V. And lastly, we learned that its magnitude is given by QVB sine theta, where theta is angle between B and V. Now, we have not discussed this, but in case you know, this entire thing can be summarized into a single expression which is given by F is equal to Q into V cross B. So in case you are familiar with cross product, the entire discussion can be summarized into this single expression. But if you are not familiar with cross product, then everything you need to know we have already discussed in parts. Right. Next, we'll not prove this, but I'll just tell you this as a fact. Whenever a charged particle is thrown in a region with magnetic field, there's only one path that it can follow, and that path is a helix. This animation shows the path of a charged particle moving in a magnetic field, and the path that it traces is what is called as a helix. To imagine a helix, think of a spring. A particle moving along the spring will basically trace out a helix. Now, if the helix has zero pitch, the pitch being the distance between 2 points as shown in this diagram. So if the pitch is zero, in that case, the path is simply a circle. Right. So the key thing to remember here is that the force is always perpendicular to velocity as well as the magnetic field. In fact, the force is perpendicular to the plane that contains these two vectors. And finally, the magnitude of the force is given by the expression QVB sine theta. Right. So this brings us to the end of this session. In the next session, we will talk about the force on a current carrying wire. Thank you.